So this is a spectrum of an astronomical object showing UV spectrum of basically hydrogen. It's got a few other things in here, like one argon line and some HD lines, which we'll come to in a minute, or a few minutes. And what I've got is a short problem here on how to, this is essentially reverse engineering, has to be said, because spectra don't appear off the telescope ready assigned like this. You have to assign them. And to assign them, you need to know the data I'm going to derive from the spectrum. So we're going backwards here, but it's a way of hopefully helping you understand how these things are comprised of. So for the moment, we're just going to worry about the lines which are labeled H2. And they have these number below them in brackets, which is the vibrational assignment. So it's V prime, V double prime. So what you'll notice is that all the vibrations are starting the vibrational ground state, and then they're going to V equals 4 and V equals 5. Then after that, we have the rotational labels, which are telling you again the J in the brackets is the starting level. So R0, for instance, is starting from J equals 0 in the lower state, going to J equals 1 in the upper state. P1 and R1 both start from J equals 1 in the lower state. And what I'm saying is that if you know what the rotational constant of hydrogen is 62 wave numbers, that allows you to give the rotational state energy levels for the ground state, and we need them up to 5. And then we can derive energy levels for the upper state by knowing these wavelengths. And I guess that involves converting wavelengths into wave numbers. So we might get someone to compute that for us in a bit. So to start off with, what I just do is derive, so we need to know for the ground state, we need to know the first 5 energy levels. Okay? And the first one is very easy, because by definition it's 0. And then we just need to know our 62 times table, which I'm sure you didn't learn at school. So 2 62s are and another 262, that's 248. Sorry. There's no easy way of rubbing out single items on this thing. 352, 476, and I'm doing that plus that's 0. 500 doesn't seem right. Got that wrong. 5/4. Yeah, 1 upon 500 is 125. Sorry, I've done this wrong, haven't I? I've been adding 2b to everything instead of 2bj to everyone. So let's scrub that. Do this again. I knew it wasn't right. So X state, J equals 0 is 0, J equals 1 is 124. The gap is then 2bj, where J is the upper state. So that's, sorry, J equals 0 is 0, J equals 1 is 124. J equals 2 is 2bj, so it's 4 times that, which is 256. That's 124. Sorry, 348. 248. You sure that's right? That's what I had before. Is that right? That makes these 2 gaps. Yeah, it is. Sorry, it's yeah, the 2 gaps are constant. Sorry, so my original thing was right. Sorry, got myself confused. Do you want to read out the numbers to me then? I don't have to do them again in my head. Do you know the other ones? 372. Is that right? 496 and 500, 600. No, 600 something. J equals 5 is 620. Is that right? Is that right? These are all centimeters minus 1. Okay, anyone a dab hand at turning wave numbers into... so the formula I normally use is that 10,000 centimeters is 1 upon lambda in microns. This is an angstrom, so angstroms to microns is factor of 100, I think. Factor of 10 to the 4, yep. So we'll need values for here, 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 here. They're not going to be terribly precise, but don't worry about that. We will need the HD ones in due course. So just one line. Yep. So are you doing them? Can you read them out for me? Okay. Yeah. Draw the picture and we'll zoom it back out again when we get on to the question. Oh, haha. Going to lose these numbers, folks, because I'll only zoom them in on the screen if I clean this. So someone make a note of them, we'll put them back up again. Is that better? So I think we're going to have to drive the numbers first and then shrink it down and then write it on them. Otherwise, when I shrink it down, I'll lose them all again. So someone put their hand up if they think they've got the numbers, just so I know when to do it. So we basically don't need the argon line. It's the only one we don't need, and then we need approximate values for all the other ones. And you'll find there's a technique called combination differences, where if you know the lower state energy levels and you have transitions to a common upper state, you should get the same answer. So that'll give us some idea of the accuracy with which we've done the calculations. Besides being a method of checking assignments, it's also a method of actually learning about the accuracy of your spectrum. You doing my numbers for me, are you? Not very far yet. Someone computing numbers for me. Sorry, we'll do it. Okay, how far have you got? I have no idea. Yeah, that's right.
Yeah, that's right.
So we've got someone starting from this end. This is doing it. Can you start from this end? So this one is 9. Sorry, I realised I need them all, because if I start writing here and then I shrink it, I'll lose the numbers. So I think that's right, but can you just write them down and I'll put them on there? You understand me? I can't put them on the screen now, or I'll just lose them again. So if you write them out on a piece of paper, and then I'll shrink the screen, and then we'll put them on, okay? But if someone can start at this end, we can meet in the middle, and hopefully half the time.
We are supposed to note down these.
I'm hoping, I think some people are calculating the wave numbers of these wavelengths. So we need them, we can't do the problem in wavelengths, you have to do the problem in wave numbers. So if someone's got a complete set, yeah, okay, we'll go to. Right. So do you want to dictate them to me and other people can tell if they agree? So this was 9, 4. Again?
5, 4, 6, right?
Come on. 9, 5, 4, 6, 5. Sorry, that's terrible. Let's try again. 9, 5, 4, 6, 5. That's better. Next one.
Next, 9, 5, 2, 8, 3.
9, 5, 0, 8, 3. 2, 8, 3. Okay. Next one.
9, 5, 2, 3, 8.
9, 5, 2, 3, 8. Next one.
9, 5, 1, 4, 7.
1, 4,
7.
7. Next one.
1, 0, 2. 0,
0, 9, 9.
1, 1.
1, 1.
9, 4. 9, 4. 9, 4, 8, 7, 6.
And the HD one.
9, 4, 8, 5.
9, 4, 8,
5, 4.
5, 4. Right. Do other people broadly agree? Roughly. This is not super accurate because we haven't got proper measurements and we've only got scales for 3 figures, but just roughly. We'll see how accurate it is in a minute because when we do the combination differences. So I now need to re-put up my J's for the 3rd time. Okay, these are all in centimeters minus 1. If I was a good boy, I'd be putting centimeters minus 1 everywhere. But space and other limitations mean I haven't. Okay, so then what we can do is, starting at the low wave number end, we've got a R0. So we can go to the state. So I'm going to write states in the upper state. There will be written as Vj. So we can get a value for 4, 1, because we're going from R equals 0. The R0 line gives you to J equals 1 in the upper state, and we're going V equals 4. So it's simply that number there. So the value estimate for that energy level is 9, 4. Sorry, I'm starting off with HD. Forget that. Start again, over here. So we're doing Vj in the upper state, and actually we should start here. So that V4J0 is at 9, 5, sorry, J1 is at 95283, and this one gives us Vj0. So that's 95147 minus 124. So V40 is 95114. Is that right? Have I done my maths right? People yell if I haven't. So that's 4. So we've done these 2 lines. P1 line. Sorry, we've done these 2 lines. Let's tick them. We've done those 2 lines. R1 will take us to 4, 2. And we have to add 124 to this number. So that'll give us 9, 5, 2, 5, 2, 6, 3, 6, 9, 5, 6. 95362, I think. R2 will take us to 4, 3. And that'll give us 95. Sorry, did I have the wrong number here? So my energy levels don't look right. What am I doing? I'm doing R. That was R1. I should have added 124 to it. I have done. That's R2. Sorry, I'm going to start this again. So you need E upper equals the wave number minus E lower, which is 0J, okay? So we do R0 first. Sorry, we do R1 first because that'll give us the V equals 0, J equals 0. And we have to subtract 124 off that number because we're starting at 124. No, you have to add, sorry, you start at, yeah. No, we're going from 0. Oh, sorry, I'm confusing myself horribly here. To get J equals 0, we need P1. That's right. And for that, we start at J equals 1 and we go to J equals 0. We had to subtract 124 off this number. So that's 95045. Okay? So we've done that one. To go to R1, we start from 0 here, so that's just the number. That's 95283. To go to J equals 2, the R1 value will work, and then we're starting from J equals 1. So we have to add onto J equals 1 to this value. So that gives us 124 onto that, will give us 952. 956362. Still doesn't look quite right, but let's worry about it in a minute. R2 will go to J equals 3, and we have to add on the J equals 2 level. Start off with, that's 248. So that's 0, 241, 2. No, this is not, I'm not doing something wrong here, or we've done the calculations wrong because that's not working. Because our J equals 3 cannot be below J equals 4. Actually, it can be below J equals 4 if you have a band head, can't it? So maybe I'm all right. Let's carry on, because these are getting closer, so maybe it's all right. Okay. P5 will give you J equals 4. And to get J equals 4 from P5, you have to subtract. So you start from P3. Sorry, 1 minute, let's start again. You start from P5. You start from here, so you add 620 on it. So you add 620 onto that, which is 95631. We've got something wrong here because they're lumpy. But let's carry on for a minute. Oh, that's J equals, sorry, that's V equals 5. That's why that's different. That one is P2. So that gives you J equals 1. And you should add, that should be 94944 plus J equals 2, which is 248. Gives me 29949. And that should be J equals 1. up here. So that is not the same number, so we've not done this right. Anyone spot what I'm doing wrong here? Because they're coming out lumpy. We can do Rx3, so that should be the j equals 4 level, and that's v equals 5, j equals 4. So this one should be v equals 3, v equals 4, j equals 4. You start with R3, you get to, so that plus 372 gives you, I've got too many figures here. Calculator, I've got 6 figures here, it should be only 5. So that can't be right. 9, 4,
8, 7.
That's an extra 4 in there. So we want to add j equals 3 to that, which is 496. So that gives you 2. 7 carry 1, 5, 3, 9, 5, 3, 7, 2. So these are not a smooth series, so I've got something wrong. And the last one I've got is a P4 for j equals 5, so that's not going to help. That'll be, so that'll give you v equals 5, j equals 3. Starting from P4, which j equals 4, 496. So that looks about right, actually. That one to that one looks about right. I've done something wrong here. I'm not good at doing maths standing in front of a board with lots of people looking at me. Could I ask you guys to take 5 minutes just to check these numbers through and see if we can work out what's right. So the general principle is that the upper energy level is the wave number plus the lower energy level. And you've got one here, which one is it? P2 and R0 should give you the same answer. They should give you both an upper energy level of j equals 1. So those two should give you the same answer. And are there any other pairs here? R3 and P5. No, they're different vibrational states. R0 and P2. There isn't a P2 here. So I think it's only those two that should give you the same state, which is the one I got here, and I got different answers for. Right, I'm going to put a different colour on here. So which line are you talking about? Say it again.
You have added 9, 4, 9. Here you have added.
So you always add.
For P.
And I've subtracted some of it. You should always add. You start from a lower level and you go up to a new level. That's all there is to it. So you should always add. I may have subtracted by mistake. I've certainly made a mistake somewhere, but you should always add. Because you've got ladder levels given here. You take a photon up to a new level, and that's all there is. It's always adding. There's some numbers. And I was incompetent at adding two numbers together, but I can't take that one. Anyone got numbers for any of these things? I see various people fevering away. See if we have some numbers somewhere. No?
So for,
Yeah.
I'm not sure it's correct, but
Okay, let's try.
for j equals 0, we have 95147.
J equals 0, 95147. Okay.
For j equals 1, we have 94978.
94978.
978. That sounds like it's going the wrong way to me.
For j equals 2, it's 95531.
5531.
For j equals 3, it's 95554.
9554.
For j equals 4, it's 95.
This is v equals 4 still? You've got j equals 4 for v equals 5 and v equals 4.
Yes, it's v4. It's 9537 for v4.
Right, so beat with that. Yeah.
Yeah, only.
Okay. Anyone got any other numbers? Which line did you use to compute this one?
For I used R1.
R1. So because no, R1 doesn't give you J1. R2.
Oh, sorry, not R1. It's
R0 gives you.
R0. Yes.
So actually, the value should be just R0.
It's
So
947.
So this, no, this, I know what you've done for R0 because it should be this number. You're just adding zeros to the number. So the question is, when you do P1, you get the same answer.
And that's 95147 plus 124 gives you 17259. 95271, 95283. Yeah, that's probably within the area of our uncertainty. That's the same answer. So the alternative answer is 9511271 here. So you can see they were probably good to about 10 wave numbers. But after all, you've only got 4 figures down here. We've got 5 figures up here. So that probably is consistent. And then that looks right because they go up. No, that's gone up a lot. That one doesn't look right. That one looks right. Anyone else got any numbers you can add to this? No one else doing it? So all you need to do is add whatever j is here to the number we've got for the wave number. So I'm not convinced all the wave numbers are right either. Because they don't seem to go monotonically, because that's 147, that's 162, that can't be right. So part of the problem is that these should be decreasing monotonically across here, but these two don't seem consistent. So I'll move on for this because the next bit, so basically you should get a set of energy levels out of here. We've got them, they're not all right and they're going to be noisy anyway because it's not an accurate measurement. But we've got j equals 0 at 95147, and we've got j equals 1 at 95280 roughly. Sorry? Okay. So that's j equals 0, and we've got j equals 1 at 95280, roughly speaking. So if we subtract those two, sorry, put them the wrong way up. We have to take the bottom one off the top one. We get roughly 133. And if we take the half of that to get the rotational constant, we get B is about 66 wave numbers, 66 or 67 wave numbers. So we've got a slightly bigger rotational constant in the ground state, which is 62 wave numbers. And that's what we're expecting. It should be a bit bigger. So you're asked to estimate, sorry, I can't do that. I have to do it here. As soon as I do anything, all these numbers are going to disappear. So if anyone's got any questions on the numbers, now speak, as it says in the British Marriage Service, speak now or forever hold your peace. Right. Yeah.
This problem from the beginning of stage.
Right. So what you have is the energy levels for the ground state. Okay? We only need V equals 0 for the ground state. So I've got the first 6 rotational energy levels. The upper state energy level, which I'm labeling Vj for the upper state, for vibration and rotation, is equal to omega. So this should be single prime, omega Vj prime, V double prime, J double prime, that's always 0, plus the energy of the lower state. Okay? So you start from a lower state, you jump up by a certain amount, you get the upper state. And if you have two states like here, J equals 0, J equals 2, and they both go to J equals 1 in the middle, in the upper state, then the difference between this and this should roughly be the difference between these two rotational levels. Well, it'll be that difference within the uncertainty that you're working on. That's what's called the combination difference. So actually, people already asked, someone asked me at the chai break how you assign a spectrum. And this is one of the methods you check for combination differences. If you know the lower levels, you can check that when you go to an upper level, the difference between the energy level, difference between the transitions satisfies this difference. Does that make sense to you? Any more before I get rid of this? You're going to be examined on this at 11 o'clock tomorrow morning, so. And you've already told me that you know everything else about the course perfectly, so this is the only thing left to talk about. I can tell that you know everything perfectly because I received 0 emails over lunchtime. So your knowledge about everything is perfect. So before I press a button, I just have to press this button here and it'll disappear, and then we can see the rest of the question. Is there any other queries about this? I'm not sure that taking photos of this is going to help me very much. There's a lot of random jottings on the screen. Okay, gone. So let's go up a bit. Right, so we had a combination difference. We found that there were 10 wave numbers off. What do you think the source of errors in this estimate of 10 wave number differences? And I can think of 2 strong and completely independent sources of errors here. So there's more than one answer to this. So when we got the J equals 1 level, they differed by about 10 wave numbers, which I said was probably meant we'd done it correctly. So why weren't they exactly the same? I can think of at least 2 reasons why they weren't exactly the same. Any offerings? What's the problem? Why is this not very accurate? Suggestions? I'm not going to be here tomorrow morning to tell you the answers, so you're going to have to think about this. Sorry? So, yeah, what do you weigh optical reasons? So the accuracy you're measuring that spectrum, you need or? Right, so what you're getting at here. This is not a high accuracy measurement scale, which in a sense is optical reasons, so I don't know what that's what you need. So this is
fairly low accuracies. You know, for astronomical standards, it's a brief and accuracy spectrum. In
terms of molecular physics, where you're trying to do things with many figures, this is not a terribly accurate spectrum. So the estimates we gave are the wave numbers, particularly by the time we'd had to guess them without measuring up on the scale properly, were not very accurate. We gave 5-figure numbers because they were 5-figure numbers, but they're probably only 4-figure accuracy. So that's one source of error. The other error is to do with the physics we used. That phrase there, assuming H2 is a rigid rotor. So we made a nice little ladder of the rotational energy levels, but nothing is a rigid rotor, and H2 is particularly not rigid. So that's also again, so when you're doing combination difference and you use one upper level and one lower level, the lower level is going to be more accurate than the upper level because you get a bigger centrifugal distortion. So that's also going to give you, that's a source of error. That source of error you can get rid of by using the proper energy levels. The other source of error is inherent to the spectrum. Okay? Right. So the last thing is not a quantitative thing, it just says we got this HD line. We've got this HD line if we want to estimate the shift from the H2 line. So we got this, oh, sorry, I didn't move it because I didn't do this. There we are. So the HD line is R040 and the H2 line R040 is there. And of course we got rid of the numbers, but they're about 6 angstroms apart. So quite a significant shift in them. What would you have to consider in terms of changing in energy? And there's more than one answer to this. You have to consider more than one thing. So if you remember a vibrational spectrum, sorry, a vibronic spectrum, rho vibronic spectrum even. So these spectra are called rho vibronic. It's a so-called portmanteau word where you've added rotational, vibrational, and ronic for electronic. So it's not very beautiful, but that's what it's called. So this means rotational, vibrational, electronic. So we have a rotational energy plus a vibrational energy plus electronic energy. Okay? Do you remember how what we've done is change the reduced mass? So the old reduced mass in integers, so mu h2 is 1 times 1 over 1 plus 1 equals a half in Dalton's atomic mass units. The new one for HD is 1 times 2 over 1 plus 2 is 2/3. So that's quite a big shift. Do you remember how the rotations depend on the reduced mass? Inversely, yep. So this depends on 1 upon mu, or 1 upon mu, the ratio of the mu's. How about the vibrations? Square root, that's right. So it's 1 upon, so let's call this mu to the minus 1. This is mu to the minus a half. I didn't actually discuss this. For those of you who know some quantum chemistry, if you assume the Born-Oppenheimer approximation, this is 0. So the electronic transition, the only effects are non-Born-Oppenheimer, which is probably for HD are not that small actually, but you normally assume it's nothing. So it's approximately 0. So you get a contribution, big contribution with the rotational change, but it's a small number. You get a reasonable contribution with vibroral change, that's an intermediate number. And you only get a very small change for the electronic thing, even though that's the biggest number. So those are the 3 contributions. I think that was the end of the question. I'll just check. Yep, that's the end of the question. Okay, so any more questions on this in particular or electronic spectra in general? They are quite complicated, as you probably gathered. So actually it's break time officially, I think.